Okay, so the last group of compounds that we're going to look at in this year's chemistry course of organic chemistry are the alkynes. And the alkynes are those carbon compounds where there is the presence of one or more triple bond between carbons. So if we notice a triple bond anywhere on the chain, we change the ending of the name to YNE. All other naming rules stay exactly the same. So therefore, if you can name an alkane and an alkene, you can easily name an alkyne as well. There's very little in this section really. It's the identification of just one member. I'm going to bring you through how to draw them and how to name them. It'll never be asked in the exam, but I think it's just important to see that the rules stay exactly the same. And also then, when we are dealing with the one member, which is the first member of the alkynes, methine, no, doesn't exist. Meth means one carbon. How can you have a triple bond between two carbons if there's only one carbon allowed? So there's no such thing as methine. So similar to the alkenes, the first member of the alkynes is ethyne. And I'm going to bring you through maybe just a little bit about ethyne, how it's made in the lab, because it is a practical that really we should have done. I've provided a video for you. And then the tests that we do on ethyne in order, first of all, to prove unsaturation, that there is the presence of a multiple bond. And then secondly, to show you what it looks like, that's in the video. And also to show you how it burns, because it's one of the most interesting combustions we have. Because the carbons have 3 bonds between them, when you burn ethyne, you actually get radical amounts of raw soot. So this gives huge amounts of soot into the classroom. Quite impressive. We will do it, please God, when we get back to class. So the alkynes, we said already, has the presence of a C triple bond C somewhere within the molecule. And that triple bond, remember, there are 6 electrons in there. So it's really rich in electrons. I told you before, there's only need for 2 electrons to hold 2 carbons together. So because there are 6 electrons here, again, there are 2 bonds that could, in theory, donate their electrons to provide, this one here could break and provide 1, 2. This one here could break and provide 1, 2. So therefore, alkynes can actually provide 4 extra addition sites, where we could add extra hydrogen, or we could add extra chlorine, or we could add extra hydrogen chloride. Whatever we need to add across that triple bond, we can do it as an addition reaction. So just to remember, there are 6 electrons between the 2 carbons in the alkyne. So it's an electron rich area, and it has the ability to donate 4 of those to spaces where other atoms or other radicals can add on. How does it look like? Well, there it is. There's your carbons. There's your C, C, H, H, and then you've got your triple bond, which is between the 2 carbons. So that's the structure. That's a very, I suppose, primitive structure, but nonetheless, it gives you an idea. 2 electrons there, 2 electrons there, and 2 electrons there. That's your 6 electrons altogether. Highly unsaturated. That word is extremely important. Unsaturated simply means the presence of a multiple bond. That's all it means. The presence of a multiple bond. Now by multiple we mean either a double, or in this case with the alkynes, a triple bond. Okay? They all end in YNE, so ethyne, propyne, butyne, etc. And their general formula is CnH2n minus 2. Now that's interesting because you're probably asking yourself, how am I going to remember all the general formulas? Well, let's just go back over them again. Let's go back over the alkenes, and then the alkanes, and now the alkynes. If you remember, the alkanes had a formula CnH2n plus 2. See that? This one here had CnH2n, and now the alkynes are CnH2n minus 2. So if you think about it, CnH2n, they all have that. That there is in all of them. But for the alkanes, because we have the maximum amount of hydrogen present and it is completely saturated, we have a plus 2. Alkenes, they lose the plus 2, and alkynes go down to minus 2. So therefore you simply drop by 2 as you go down through the general formula for each of those families. Alkanes, CnH2n plus 2. Alkenes, CnH2n. Alkynes, CnH2n minus 2. So you simply drop by 2 as you go down through the group. So if you want to remember the alkanes as CnH2n plus 2, and then drop down by 2 for each of the following alkene and alkyne unsaturated homologous series. Okay, so there's the way we would draw this thing, with the 2 carbons, with the 6 electrons between them, which is formed in three covalent bonds, a triple bond, and the 2 hydrogens. The only alkane, or alkyne I should say, we have to worry about is ethyne, all right? But it has another name. It's called acetylene. Now, some of you may have heard the phrase before, oxyacetylene. Oxyacetylene is when you take acetylene, which is ethyne, and you add oxygen to it. And there's a video down here that you can look at yourselves. It'll show you how effective these 2 gases are together when you burn them. But you've got ethyne, and then you add oxygen. If you get the combination just right, you can get a flame that can cut through metal like a hot knife through butter. Okay, it's extremely hot, very, very hot flame. If you don't get the ratio between the ethyne and the oxygen correct, you'll end up with an explosive mixture. And there are plenty of videos out there. You can look from yourself on Google, look in burning ethyne explosion, and you'll see exactly what it can do to a fume cupboard if the ratio between the ethyne and the oxygen is not correct. So this is the only one I actually worry about in the lab when we're doing it, is that when we burn a gas jar of ethyne, we've got to make sure that the oxygen-ethyne ratio is not at that explosive mix. So we never use the first gas jar, because there'll always be air, residual air in there. We use the second or third one. And to date, thank God, we've always had a brilliant combustion experiment where we get copious amounts of soot and a little bit of water vapor in on the sides of the gas jar. So that's the structure, as we said already. It's used in oxyacetylene. This is its major use. Now, oxyacetylene is nothing more than a mixture of ethyne and oxygen. Okay, just keep that in mind. It's ethyne and oxygen. It's called oxyacetylene, and when you burn it, you get a very, very high flame. You can weld metals together, and you can cut metals. All right, so you often see a blowtorch. With these blowtorches that weld or would cut metal, they would have ethyne in one tube, oxygen in the other tube, and a control valve between the two that would allow you to get the ratio correct, so that you can get this flame up to such a high degree in temperature that it'll weld metal or cut metal for you. 3000 degrees is what we're talking about. So much hotter than your ordinary classroom Bunsen flame, and that's hot, but this is 3000 degrees. So do have a look at that video. It'll give you an idea as to what the ability of oxyacetylene is to cut through a thick lump of metal. Okay, so how do we prepare this gas? Now, this is examinable. You do have to know this. This is something we do have to do in the classroom. We will, please God, when we get back, look at the preparation of ethyne. But for the moment, let's just go through it in theory. Ethyne is prepared by reacting water, that's going to be your liquid, with calcium carbide, which is CaC2. Now, when we get CaC2 brought into the lab, it contains very many impurities. So the first thing we're going to notice when you open the lid on calcium dicarbide is the smell. It actually smells quite sulfuric. It smells quite bad, okay? Almost like rotten egg gas, but not that strong. But there is a very, very definite smell of it. What you're smelling are the impurities. It's a very impure substance. But when you look at it, it looks for all intents and purposes like sand. Or it might look like little rocks. Or some people will actually tell me it looks like, if those of you who burn a solid fuel fire at home, when you're taking out the ashes, it looks exactly the same as that. Kind of a brown powder with little black flecks through it. Looks very similar to that, but it is extremely impure, and those impurities are going to cause a bit of a problem in our collection, but we'll deal with those later on. The C2H2 produced is usually contaminated with, now this is dihydrogen sulfide, which is better known as rotten egg gas, so that's quite a smelly thing, phosphine and ammonia. So these three impurities are present in the calcium dicarbide when I buy it. So when I go to use it, that's the first thing you'll notice is the smell of it. So keep in mind, and you do have to know what the impurities are, dihydrogen sulfide, this thing here, phosphine, and this thing here, everybody should know at this stage, ammonia. So ammonia has quite a pungent smell too, so it's quite a smelly substance. The chemical reaction is as follows. When you take the calcium carbide and you add water to it, these two will react to give you the ethyne that you require, and then calcium hydroxide, which will, for all intents and purposes, appear like a kind of a cloudy liquid at the bottom, and it'll have a fairly high pH. So you can test it as well with litmus paper, universal indicator paper, if you wish to see exactly what its pH is. But it's quite a basic solution. So calcium carbide with water gives me the ethyne gas and calcium hydroxide. Now you do have to remember that balanced equation. So maybe just write it out a few times, 5 or 6 times until it gets into your head so that you know what the balanced equation is. Here's how we prepare it. Very similar to the way in which we collected Ethyne, except we're dropping the water down through what we call a delivery funnel or a dropping funnel onto the calcium dicarbide. Now we do it quite slowly. In fact, we do it drop by drop because the reaction between the water and the calcium carbide is quite a fast reaction, quite a vicious reaction. It really gives a lot of gas very, very quickly. So we drop the water on slowly but continuously. That's the key thing. So slowly but continuously. And we drop down here, and what you'll notice is straight away you'll start to get the bubbles, as you can see there, coming up through the water and pushing the water downwards as we collect it. Now we had this with Ethyne. If the bubbles of Ethyne pass through the water and come out the other side to be collected, then we know from that C2H2, that Ethyne itself is not soluble in water, because if it was soluble in water, the bubbles would disappear, would dissolve in the liquid, and we wouldn't be able to collect them. So C2H2, the Ethyne itself, is not soluble in water, and we've got to know that. And secondly, we're collecting this again by the downward displacement of water. Okay, so that's what we need to remember. Dropping water onto calcium carbide, so you're dropping your H2O onto your CaC2. You're getting a chemical reaction which involves the Ethyne, the C2H2, through water, meaning it's not soluble in water because it passes straight through, and then by the downward displacement of water, and we fill this gas jar to the brim. Normally we collect about 3 of them so that we can test on them afterwards. You do have to know this diagram, you do have to be able to draw it. But there's one small thing that we need to be careful of, and here it is. Remember I told you that the calcium carbide is very filled with a lot of impurities, yeah, very impure. When the gas passes through, these impurities are going to come with it. So what you gather here is Ethyne gas with all the impurities that you don't want. So what we could do is we could break this tube here and pass the gas through what we call acidified copper sulfate. Now, what the copper sulfate will do is it will act like a sponge, and it'll draw all the impurities away from the Ethyne gas. It'll leave the Ethyne gas alone, so that if you put that here between where the reaction takes place and the collection takes place, then as the gases pass through, all the impurities will be taken in by the copper sulfate, and the Ethyne gas, which will be purified, will then be collected here. Far better way to collect Ethyne gas. Little bit more difficult to set up the apparatus, but they can ask you sometimes, what change could you make to the apparatus to ensure that your Ethyne is pure? And the answer would be, between the reaction vessel and the collection vessel, put in a bottle of acidified copper sulfate and pass the gas through it. The impurities will be removed and the Ethyne gas will be purified. Okay, so we have that there. Just let me take off my notations. So we have it there. Ethyne gas is collected by the downward displacement of water, and it shows also by the bubbles that it is not soluble in water. Okay, now the Ethyne produced, as we said already, contains many impurities, and it has a pungent odor. So the first thing you notice, if you were to take off the lid of a gas jar and waft it, dreadful smell. That's not the Ethyne you're smelling, because Ethyne itself doesn't have a smell. I mean, if it does, it errs on the side of being more pleasant than pungent. So if we want to get rid of the impurities, we bubble through copper sulfate. So here we'd break it and we bubble it through a beaker of copper sulfate, let it go through, the impurities be pulled out, and then the gas up here would be purified. And again, you can watch the procedure in this video here, and that'll bring you through the preparation. Okay, so what are its properties? Well, first of all, like Ethyne and ethane, it's a colourless gas. That's the first thing you'll notice. And again, if there is to be a smell, you can call it sweetish. It's pleasant, it's not pungent, all right? It is insoluble in water. We know that because we can pass it through. We actually collect it through water, which means it's insoluble in water, and it burns with an extremely smoky, luminous flame. Now, you'll see that down here. They actually show you what it looks like when you burn it. Luminous means you can see the yellow flame, but smoky means a lot of black soot a lot of black carbon produced as it burns. It decolorizes bromine water, and it also decolorizes acidified potassium permanganate. Now, we told you this before, and I want you just to remember what the colors are. Bromine water is yellow. Okay, it's a yellow liquid. Potassium permanganate is a purple liquid. Now, the lovely thing about both Ethyne and Ethyne, because both are unsaturated, is that when you pass the gas through them, both of these will become colourless. They will lose their colour straight away, because as I told you before, in Ethyne the double bond will open up, or I should say one part of the double bond will open up and allow the bromine to add across, which means the bromine is turned into bromide and it loses its colour. With the potassium permanganate, also we get an opening of the double bond, and we get a changing of the Mn+7, which is purple, talk about that later, into Mn+2, which is colourless. So that's why the colour change takes place. Don't really worry about that just yet. All I want you to remember is the following for Ethyne. It's a colourless gas with a sweetish smell. It doesn't dissolve in water, so we can collect it through water. It burns with a very smoky luminous flame, and it decolorizes two things: bromine water, which is yellow, and acidified potassium permanganate, which is a dark kind of a purple colour. So let's just take a look at some of these questions here. I'm going to do one of each and leave you the second one to do yourselves. The alkene CH3 twice CH, CH2, CH double bond CH2 is named 4-methyl-1-pentene, or as we would say here, 4-methyl-pent-1-ene. What is the name of CH3? Now I think just draw it. Let's have a look at it and see what it looks like. So what have we got? These are branches. So you have a carbon which will have two CH3s like that. Yeah, and then we have another carbon which has two hydrogens. Then we've got the triple bond C, and we've got a final H over here. So that's the way this looks. Now, what's this called? Well, let's take a look and see. 1, 2, 3, 4, 5. Yeah, so we still have pent. 1, 2, 3, 4, 5. So this is pent. There's a triple bond, YNE. It's after the first carbon going this way, because we give it the smallest number, so it's pent-1-ine, and then 1, 2, 3, 4. On the fourth carbon, there is a methyl group. The more of this practice you get, the better. So it's 4-methyl-pent-1-ine. Okay. Draw the structure for each of the following compounds. Now, acetylene, as I told you already, that's its common name. It's also known as ethyne. And that's easy enough to draw because that's the molecule we're dealing with. It's that. 1, 2, 3, 1, 1. And then 3-methyl-1-hexyne. Now let's start here. Hex is 6. 1, 2, 3, 5, 6. Hex 1-ine. That means that the triple bond is going to be here after the first carbon. And on the third carbon, there is a methyl group. Done. So I'm going to leave you with the rest of these in question 2. But I'm going to do the last part of question 3. Name each alkyne. 1, 2, 3, 4, 5. Now, I think it's best to draw this. So 1, 2, 3, 4, 5, 6. Let's say it again. 1, 2, 3, 4, 5, 6. No branches. How do I know there's no branches? Because there's no radicals in brackets. Okay, just be careful. There's no radicals in brackets, so there's no branches. They're straight across. Where's the triple bond? It's after the second carbon coming in from the left. So there it is there. And that's it. So 1, 2, 3, 4, 5, 6, hex. And because the triple bond is after the second one, 2-YNE. Okay, now I want to take a look at this exam question, because tomorrow I'm going to ask you, or tonight I should say, when you finish looking at this video, I'm going to ask you to go up to the top section of Google Classroom to take the 2 revision sheets that are there. One of them is on naming and drawing compounds, and the other one is on comparing ethyne and ethyne. And I want you to do both for the live class for tomorrow, Tuesday. So let's just take a look at this. This comes from the Leaving Cert directly. And it just shows you how direct the questions are and how easy they are once you understand the process. A liquid X is dropped onto solid Y, and the gas collected is in test tubes as shown. Okay, so what are we doing? We're preparing ethyne gas. So let's just highlight a few things here. This is the preparation of ethyne. So let's keep that in mind. Okay, now what are we dropping onto what? We're dropping a liquid onto a solid. The liquid is obviously water, and the solid is your calcium carbide, CaC2. So there's X and Y for 8 marks, which is quite decent for each. Describe the appearance of the solid Y. That's to make sure that you've done the experiment, that you've seen this stuff up close. It's like sand, but the biggest thing we notice about it is it's very pungent. So there's two things I want to say about this solid Y. First of all, it's kind of ashy or sandy in appearance, and it has a pungent smell. That's the key thing. All right. So describe its appearance. It's sandy. It's hard to explain, but if you take a handful of sand, it's like little rocks that are kind of sandy in color, and there are black flecks through this kind of sand, which are the impurities. Write a balanced equation for the reaction between X and Y producing ethyne. Now, let's just take it up there. What are we reacting together? CaC2, so that's your calcium carbide, and your water. What do they give? Well, obviously they have to give us the gas we're dealing with. They have to give us ethyne and calcium hydroxide. So we need to balance this, and you just have to learn this. Just learn that equation and balance it. There are 2 carbons. That's a match on the left hand side. There are 4 hydrogens, 2 here and 2 here on the right hand side. So I'm going to have to put a 2 there to bring that up to 4. That in turn gives me 2 oxygens, snap, and I've got 1 calcium and 1 calcium. That's the balanced equation. Just learn it. Write it out again 4 or 5 times, get used to it, and you'll know it off by heart. Part D. What is observed when a sample of ethyne gas is burned in air? Well, you notice 2 things. It's luminous. The flame is luminous. You can see the yellow flame. And the second thing that people always remember, it is it's a very big producer of soot. So you get a lot of carbon produced. Okay? A lot of soot, black soot. And it wants you to write a balanced equation for the combustion of ethyne in oxygen. Now that's easy, because ethyne is a hydrocarbon. All hydrocarbons, when burned in oxygen, give only 2 things: carbon dioxide and water. So C2H2 plus O2 can only give, see, there's only C and H in ethyne. So when you're reacting a hydrocarbon with oxygen, the carbon will go with the oxygen and give you carbon dioxide, and then the hydrogen goes with oxygen and gives you water. Now we have to balance this thing because all equations have to agree with the law of conservation of mass. So 2 carbons, 1, put a 2 in front of that, and then we have 2 hydrogens, match. We have 2 2s are 4, oh, and 1 is 5. Now that's the most unusual number of oxygens. 2 on the left hand side and 5 on the right hand side. So we're going to put a 2.5 here. But just remember, in chemistry, we cannot use halves. So even though that is mathematically correct, it has to be rebalanced. So let me just write that down as C2H2 twice. So I'm going to multiply everything across by 2. Plus 5O2 gives 4CO2 and 2H2O. And you'll find that that's still balanced. 4 carbons, 4 carbons. 2 2s are 4, and you've got 4 hydrogens here. And 5 2s are 10, 4 2s are 8, and 2 is 10. So the whole thing is balanced perfectly. So yes, by all means do it mathematically, but then get rid of any fractions, because you can't have a half a molecule. So therefore balance it up to be, as we said right the way back to Dalton, whole simple number ratios. Reverse it, simple whole number ratios. Okay, ethyne C2H2 is described as being unsaturated. Let me just get rid of that here. Get rid of this out of the way. And this one here. Okay, so ethyne is described as being unsaturated. Describe a test you would carry out to show that ethyne is unsaturated. Now, we've only got 2 tests to prove that it's unsaturated. Number 1, bromine water, Br2/H2O. And the other one is acidified KMnO4. This one goes from yellow to colourless, and this one goes from purple to colourless. So basically what you would say there is that you would take some bromine water, which is yellow, or some acidified potassium permanganate. You would add it to a gas jar containing ethyne, put the gas lid on and shake it. And after about 2 or 3 minutes, you'll notice that the bromine water, which was yellow, has become colourless, or that the purple acidified potassium permanganate has become colourless also. That's the most visual test we have for unsaturation. And you do know what the definition for unsaturation is? Unsaturation, it is the presence of a multiple bond, i.e. double or triple. If there's a double bond or a triple bond anywhere, it's unsaturated. Okay, write an equation for the reaction that's taking place. Now, in that case, we haven't studied this yet. That's something we'll do in mechanisms next year, so I'm not going to really worry about that. And then name the organic product. So I'm not going to worry about that just yet, but just to know we will do it next year when we're dealing with various different mechanisms in the organic families. The common name for ethyne gas is acetylene. Give one major use of that gas. Now, we had it earlier on. You saw a video of it if you looked at the video links on the slides. If you take C2H2 and if you react it in a special ratio with oxygen, you will get what's called oxyacetylene. And oxyacetylene has a flame of about 3000 degrees when you burn it. So therefore we use it for two things. We use it for welding metals together, and we use it for cutting metal. That's how powerful that flame is in terms of its temperature. So that brings you through a question in relation to ethyne. Not much to know about the alkynes, but again, take the three first homologous series together, the alkanes, the alkenes, and the alkynes, and see them as a group of hydrocarbons that have similar type of quality. They're all colourless and they're all kind of a sweetish smell, but just keep in mind how we go from one to the other. How do we go from alkanes to alkenes? How do you go from alkenes to alkynes? And the answer is by increasing the number of bonds between carbons. If they're all single, it's alkanes. If there's a double bond, it's an alkene. And if there's a triple bond, it's an alkyne. And then just to know about its properties, how it burns, how do we produce it. For ethene and for ethyne, know the chemical reactions involved, know the tests that we do on these gases after their preparation. And that's all they can really examine you on.